and we're going to get into this problem. Okay, this is the problem I said I would do at the start of class today, before moving on into the next set of material. Hydrogen may replace gasoline as a fuel in the future. Most major automobile companies are developing vehicles that run on hydrogen. These cars are environmentally friendly because their only emission is water vapor. One way to obtain hydrogen for fuel is to use an emission-free energy source such as wind power to form elemental hydrogen from water. What mass of hydrogen is contained in one gallon of water? So our compound that we're looking at is we have the compound of water, which is H2O. So we know there's 2 hydrogens for every 1 oxygen. Now let's break this down. We have been asked for the mass of hydrogen contained in 1 gallon of water. So we have 1.00 gallons of water, and we're wanting grams of hydrogen. Oh, that's terrible. First things first, I see that the 2 compounds are different. Because the 2 compounds are different, I am going to need a mole to mole ratio, which is there are 2 moles of hydrogen for every 1 mole of water. The next thing I see is I have a volume of water. One of the ways that we can work with volume is to use the density of water, because that is a way to go from volume into mass. So we are going to be using the density of water as a conversion factor, which is 1.00 grams per milliliter. Now, in order to do that, this gallon has to be converted into milliliters. So we're going to take that gallon and we're going to have to convert that gallon into liters before we can convert it into milliliters so that we can use the molar or the density. That will get us into water, but we need grams of hydrogen, and anytime we have grams, I use the molar mass. So the molar mass of hydrogen is simply 1.008 grams per mole. I may not have all the conversion factors I need, but I have a lot of them. I have a lot of them because I have taken what I was given and I have broken it down. So we begin with what was given, which is the 1 gallon of water. And I know this is very small for the back. I will blow it up and have to move along. But okay, so the first thing we're going to do is convert that gallons of water into liters of water with the fact that 3.785 liters is equal to a gallon. We can then convert that liters of water into milliliters of water with the fact that there's 1,000 milliliters in 1 liter. We can now, and from this point forward, all I've been doing is paying attention to the units and making sure that the units cancel. Now I've got milliliters of water. I can use the density of water. So that's 1.00 grams of water is equal to 1 milliliter of water according to the density. The milliliter went in the denominator, so again, that the unit would cancel, leaving grams of water. Now, it is similar to what we have been doing. What we were doing on Tuesday. So I'm going to take that grams of water and I'm going to convert it to moles of water using the molar mass of water. And this was one conversion unit I did not get. 18.016 grams of water is equal to 1 mole of water. I knew I had to have this because what is the only way to convert between two substances? The mole to mole ratio. So you had to get this into moles. So even though I did not come up with this conversion factor to begin with, my units are telling me I have to have it because the only way to convert between two substances is the mole to mole ratio. Now I can use the mole to mole ratio for every 1 mole of water. There's 2 moles of elemental hydrogen. The moles of water went in the denominator and I'm left with moles of hydrogen. But I was asked for mass of hydrogen. So my final conversion factor is 1.008 grams of hydrogen is equal to 1 mole of hydrogen. The mole of hydrogen went in the denominator, leaving me grams of hydrogen for the numerator. Now I'm ready to do this math. And when you key everything into the calculator, you get 424 grams of hydrogen. So the thing we added was the density. The thing we added was really the density. We had to do a couple of conversion factors to be able to use that density. But the thing we added was the density because density is one way to convert from, well, is the only way to convert from volume of a substance into mass of that substance. Density is the only way to convert between volume of a substance into mass of that substance. Questions? Again, I'm going to drive this home because we're going to have another volume conversion factor here in a few minutes. Well, not in a few minutes, next week. But the only way to convert between volume of a substance and grams of that same substance is the density. Okay, if there are no questions, then I'm going to delete that. It'll let me. And we are going to move on to chemical reactions with a very short discussion up front. And it's not wanting to let me broadcast properly. There we go. Okay, so we have finished our discussion about the atoms of the elements. We have finished our discussion about the compound. Now we're getting into reactions. And with the concept of reactions, we're going to talk about physical and chemical changes. Examples of a physical change include boiling water. We have been told all of our lives that we have water as a liquid and we heat it up, we get steam, which is nothing but water. That's an example of a physical change. Around this time of the season, everybody wants some dry ice. At least I like to play with dry ice. So I go get some dry ice and I see it smoking. All it's doing is sublimate. It's undergoing sublimation, where the dry ice solid is going, which is carbon dioxide, is converting into gas carbon dioxide. It's still carbon dioxide. Origami. We didn't change the paper. We just changed the arrangement of the paper. Breaking glass. Technically, we haven't changed the glass. It's still glass. It's just now in charge. Even cracking an egg. That process itself is a physical change because we didn't change the albumin, the gelatinous, clear, colorless liquid, and the yellow yolk. All of these are physical changes, which are changes that do not alter the identity of the substance. So a physical change is something that does not alter the identity of the substance. That is different than a chemical change. A chemical change causes a rearrangement of the atoms to form new substances. So we undergo a change. We are changing the substance entirely. Examples include frying an egg. Now, I said breaking an egg was a physical change, but if you fry the egg, you no longer can get back that gelatinous, clear, colorless albumin. You can never get it back. So that's a chemical change. Combustion. Anytime you got fire involved, it represents a chemical change. Because fire is some substance plus oxygen, and they go to make some new substances. So burning wood is an example. You cannot get back the log of wood. It is now carbon and carbon dioxide and water gas and all sorts of things, but you can't get back the wood. These are all examples of chemical changes. So again, a chemical change is going to completely alter the identity of the substances. Now, these changes are described by properties. A chemical property, though, you can only identify once it's undergone a change. So the fact that wood combusts, I could not have known that without actually observing the wood combusting. I could not know that iron will rust to form iron oxide without observing the iron rusted or oxidizing. So a chemical property is going to be a property that is displayed only once that chemical change has occurred. Whereas a physical property, we can describe it without the substance undergoing a change. So physical properties and chemical properties. A physical property would be luster. How shiny is it? I can describe whether it's shiny or dull without ever altering what it is. I can identify its hardness. The hardness of a diamond can be identified without altering the identity. The mass of a substance can be determined without altering its identity. Even the density. We ran density experiments earlier in the semester. We never altered the identity of the substance when we determined its density. But chemical properties, again, you can only determine those by observing the chemical chain. Is a substance flammable? Is it radioactive? When we were doing the radioactivity experiments earlier this semester, those substances like strontium and cesium, they were giving off radioactive particles. There is going to be a time where that strontium and cesium will no longer be radioactive, because all of the radioactive particles will have undergone a change. So again, radioactivity is an example of a chemical property. Whether something is corrosive and will burn, whether something's toxic. Now, pH I have a little bit of difficulty with. pH is one of those things that can be considered a physical property or a chemical property. It depends upon whether you're observing a change during the process. So let's just look at an example. Which change is a chemical change up here? The burning of lamp oil. You can't get the oil back once it's burned. Lamp oil typically is converted into some carbon, which is the black smoke that's given off, along with carbon dioxide and water. The evaporation of rubbing alcohol, though, would be a physical change, because it's still rubbing alcohol. It's just in a different phase. It's no longer in the liquid phase, it's in the gas phase. The forming of frost on a cold night is, again, an example of a physical change, because all you've done is taken the water that's in the atmosphere and you have condensed it to form a solid. But it's still water. Whoops. Let's look at this diagram. And let's identify whether it's a physical change or a chemical change. Now, what these dots represent, the blue dots represent hydrogen. So when you see two together, that means you're talking about the diatomic form of hydrogen. The red dots represent oxygen. So when you see two together, you're looking at the diatomic form of oxygen. Now, in order for it to be a physical change, it means that if it's H2, it's H2 at the beginning and it's H2 at the end. If it's not H2 at the beginning and H2 at the end, that means that it underwent a chemical change. So let's start out with this left-hand side. Going from the top bubble, to the bubble underneath. Chemical or physical? Chemical, because the H2 is no longer H2, it's now just H. So yes, when you take a molecule and you break it apart, it's undergoing a chemical change. What about now? Let's move from left to right. So this top bubble to the next bubble over. What we're making, well, first of all, is it chemical or is it physical? It's chemical because it's no longer just H2 and O2. You now have H2 still left over, but you also have hydroxide units, OHs. Let's scoot down the middle row. Going from this one down. Is that chemical or is that physical? Physical. Because all you've done is separated the two types of gas, two types of molecules. You haven't changed the OH molecules. You haven't changed the H2 molecule. So it was just physical. How about these two processes? Both of them are chemical because you're ripping apart the molecule. Finally, how about going from this top middle bubble to the top right bubble? It's chemical because you took those hydroxides and you added another hydrogen to make water. Any questions about how to identify a chemical change and a physical change? A chemical property and a physical property. Some things that you can look for, folks, to know that it's a chemical change includes formation of gases. And I'm not talking about evaporation. I'm talking about if you combine two chemicals and you get bubbles like you do when you combine baking soda and vinegar. That's an example of a chemical change. Drastic color changes. And I say drastic because you'll get somewhat of a color change when you take freshly steeped tea and you simply dilute it. It's going to go from a really dark brown to a much lighter brown. That would be an example of a physical. But if you add lemon to that tea, it changes it. It changes it. Because now you're going to have a new material and the color is going to be it's going to be a fairly drastic change. Some other things is the formation of a precipitate. The formation of a precipitate or a solid from two aqueous solutions would be an example of a chemical change. Those are key examples of chemical changes. Whereas a physical change would be like cutting a piece of aluminum foil. You got aluminum foil and you got aluminum foil. They're just different sizes now. Question? Yes. Okay, so if it's physical, it would be like taking, well, so we're going to get into a relatively detailed explanation. First of all, if I'm talking about taking my tea and sticking a pH probe in it and determining the pH of the tea, I didn't alter the tea, I just determined the pH of the tea. That would be an example of a physical property. But as we will be doing on Monday, we're going to be doing titration. And we're going to start out with an acid that has a low pH. And as we add base to it, we're going to undergo a chemical reaction and it's going to cause the pH to increase. So that's why I said that one's a little tricky. You have to think about what's going on. You can't just jump to pHs. Other question. Thank you. Also, if I look at the pH meter or the pH paper, when pH paper changes colors, it's actually the paper itself is undergoing a chemical change. Okay, why are we talking about chemical changes? Because come on. Okay. What we're getting into next is chemical equations. We are actually talking about the chemical reaction now. And you're going to see me use, when I talk about a balanced chemical reaction, you're going to see that used interchangeably with the term balanced chemical equation. Reaction and equation in this particular case mean the same thing. So I just wanted to let you know, because in the textbook that I'm following along with, it is equation. But I've always called them reactions. So the reason we had to talk about a chemical change is because a chemical change occurs via a chemical reaction. And chemical reactions are represented with the chemical equations. So we had to talk about a chemical change in order to start talking about these chemical equations. What? Cancel. Now, there are a variety of pieces to how we write a chemical equation. And folks, I've got to go back and tell this little bitty story. When we were talking about the atoms and the elements, those symbols up there are like the alphabet to chemist. That's our alphabet. When we combine those chemical symbols to form compounds, well, it's just like combining the alphabet. We're forming words. Well, when we start combining these chemical formulas in a chemical reaction, it's like writing a sentence to it. So when we get into these chemical equations, we're writing sentences. And just like, well, I don't know if they still do it. When I was a kid, we had to graph out the noun and the verb and the adjectives and stuff like that. And it had to go in a certain flow typically. Our sentences have a certain flow. They all start with the reactants. These are the chemicals that are being combined. And the sentence ends with the product. These are the chemicals that are being formed. Now, we have to have a way to go from the start of our sentence to the end of our sentence, and that is to use an arrow. Now, we're going to typically use a single-headed arrow in this class. However, when you get to college chemistry 2, you're going to find out that there's two types of arrows. There's single-headed arrows and there's double-headed arrows. They mean different things. But for the most part, we're going to talk about the single-headed arrow. And this single-headed arrow means produce. This is our verb. Another way to say it is yields, makes. Give me any other synonym along those lines. And that's what that arrow means. And as we're going to talk about, it also means equals. When we start talking about our balancing of a chemical reaction. Now, another piece to this puzzle is we want to describe exactly what our chemicals look like. And so we will include physical states after each chemical. And what these physical states are doing is they are describing what does that particular substance in the reaction look like. I'll go over those in just a minute. Now, in a couple of chapters, we're going to add one more piece to this sentence, because technically this sentence is not complete. Because every chemical reaction also has associated with it some form of energy. Whether that's the production of energy or whether that's the absorption of energy, every single reaction has some form of energy associated with it. And so when we get to chapter 9 of the textbook, we're going to add the energy action to this discussion. But for the next 2 chapters, we're mainly going to talk about the identity of the reactants and their states, and the identity of the products and their states, and then our verb produces, yields, makes, whatever it is in the line. So, those states include a solid. If we're talking about a solid, that typically means we're talking about something that has a very nice 3D array of molecules. We're talking about an organized substance, typically. When we talk about a liquid, which will represent, now, you'll see it written as just an L, but you'll also see it as a cursive L, and it's still an L. The big difference is those that are writing it as cursive are doing so to try to distinguish it from the number 1. But anyhow, it's an L. A liquid is still, the molecules are very close together, but they are more disordered. They will flow into one another. Then you have a gas. A gas means that the particles are far apart compared to the actual size of the particle. It means these particles are moving around in every possible direction and fighting with anything that they encounter. And then, though this one is not as obvious, we're going to talk about it a lot more, but I can't blow it up any further. You have aqueous. Basically, it just means that this substance is dissolved in water. So going back to our I'm stuck. So going back to our chemical equation, the ammonium ion was dissolved in water. The nitrite ion was dissolved in water. When you combine ammonium and nitrite, one product was nitrogen, which is a gas. This means that what we're going to see when we do this chemical reaction are bubbles being formed. Those bubbles are that gas being formed. And then we made pure water, which is a liquid, which we're always, so a lot of times water is going to be in the liquid format, especially if we started out with aqueous solutions. Now, chemicals must follow the law of mass conservation. I've already introduced this concept of law of mass conservation. It says that mass cannot be created nor destroyed. When we were developing the molar masses for our chemical formulas, we were adding the mass of hydrogen, a mass of hydrogen and a mass of oxygen to get the mass of water, because mass could not be created or could be destroyed. Well, when you're dealing with a chemical equation, you must also follow the law of mass conservation. So, the process, I'm going to break down the process a little bit more, but basically what you do is you start with your elements and you look at it and say, okay, on the reactant side, there is only one carbon atom in these two substances. There are 4 hydrogen atoms found in these two substances, and there are 2 oxygen atoms found in those two substances. On the product side, there is 1 carbon atom found in these two substances. There's 2 oxygen atoms found, or not oxygen, hydrogen atoms found in these two substances. And there are 3 oxygen atoms, 2 from the carbon dioxide and 1 from the water, to make a total of 3. We are not following the law of mass conservation here, because we can't mysteriously lose hydrogen. We can't mysteriously gain oxygen. So we're not following the law of mass conservation. Now, to balance a chemical equation, in order to follow the law of mass conservation, we are going to adjust the coefficients. Those are going to be numbers that are going to precede the chemical formula. Right now, since there's no number shown, that means there's only one of those. But we are going to adjust the coefficients. So it's going to be the number in front of the chemical formula. Do not touch the formula. You cannot adjust the subscripts. You do not touch the formula. All you can do is adjust the number that precedes the formula. So in order to balance this chemical equation, what we're going to need is we're going to need 1 methane, 2 oxygens, 1 to produce 1 carbon dioxide, and 2 water molecules. To prove that this is a balanced chemical equation, we can do the same thing we did just a moment ago and go, okay, we have carbon, hydrogen, oxygen. On the reactant side, we have 1 carbon, we have 4 hydrogens, and we now have 4 oxygens because there are 2 O2s for a total of 4 oxygen atoms. On the product side, we have 1 carbon. We now have 4 hydrogens because there are 2 H2Os. So there are 2 times 2 or 4 hydrogens. And there are 4 oxygens because there are 2 in the carbon dioxide. And then since we have 2 water molecules, we have the other 2. Yes. No. The formula for the hydrogen, if we go back, we started with H2O. We still have H2O. So we did not alter the formula. All we did was alter what was preceding the formula. Other questions? So what's the process? This is where you coming in prepared is going to make me a lot faster. And I want that to start on Tuesday. Because then I can just read this and move on and not give you time to write. Because it'll already be written. The first thing we're going to do is we're going to write an unbalanced chemical reaction. just like we started with our methane combustion reaction. We're again going to balance the atoms that occur in more complex substances first. I balanced the methane first because it was more complex than O2. We will always balance the atoms in compounds before we get to the pure elements. O2 is going to be the last thing we balance in a combustion reaction. Why? Because we can put what subscript we need in front of that, and we're only impacting one element. So let's continue this how-to. Well, I just said we balance atoms that occur in free elements on either side of the equation last. That's because we can put any coefficient there that we need in order to balance the equation. If the balance equation contains coefficient fractions, then we have to get rid of those fractions. And you get rid of the fractions by multiplying through by the denominator of the fraction. Now, once you've balanced the chemical equation, it's always important that you check your work. Did you balance it? You've noticed I went in and I listed out that CHO again, and I said there were 4 atoms of, 1 atom of carbon on the reactant side, 4 atoms of hydrogen, 4 atoms of oxygen. And I checked that with the product side. You always should check your work. And then the last thing that you should do is you should make the coefficients as small, they should be the smallest whole number ratio possible. Your coefficient should be the smallest whole number ratio possible. What do I mean by that? Going back to the methane example. If I would have finished the problem and I had 2 methanes and 4 oxygens and 2 carbon dioxide and 4 waters, all of those coefficients can be divided by 2, so I would have simplified the problem. Because the balanced chemical equation should have been the smallest whole number ratio possible. So let's balance some equations. Now, one trick that if you watch my flipped videos, you would know that I do, is I do a cursory glance through the entire problem. And when I'm doing this cursory glance through the entire problem, one of the things I'm looking for is polyatomic ions. I'm looking to see, okay, I have a polyatomic ion on the reactant side. Is the polyatomic ion the same polyatomic ion on the product side? If so, when I'm making my list of things, I keep that polyatomic together. That is going to simplify your life a lot if you will do that. So again, I do a cursory glance and I look for mainly polyatomic ions. In this particular case, I see, oh, wait, I have phosphate on the reactant side and I have phosphate on the product side. When I'm making my list, I'm going to keep that phosphate together. So I'm going to list out the strontium, the chlorine, the lithium, and the phosphate. On the reactant side, I have 1 strontium according to the formula. I have 2 chlorines. I have 3 lithiums, and I have 1 phosphate. On the product side, I have 3 strontiums. I have 2 phosphates. I have 1 lithium and 1 chloride. This is not balanced. Therefore, I'm going to start balancing. And in this particular case, it doesn't really matter which one I start with because they're all about the same complexity. So I'm going to start with this strontium and balance that strontium. So in order to balance it, I'm going to multiply the left-hand side, the reactants, by 3. Whatever you multiply by becomes the coefficient. But what happened to my chlorine when I made the strontiums balanced? I tripled the chlorine. I now have 6 chlorine atoms, not 2. The next thing I'm going to balance is, why not, my chlorine. On the reactant side, I have 6 chlorines. On the product side, I have 1. To balance the product side, I have to multiply the product side by 6. Whatever you multiply by becomes the coefficient. But in giving myself 6 chlorines, what did I do to the lithium? I also made it 6. Next thing I'm going to balance is the lithium. On the reactant side, I have 3 lithium. On the product side, I have 6 lithium now. To balance these out, I've got to multiply the reactant side through by 2. Whatever you multiply by becomes the coefficient. And in giving 6 lithium, what did I do to the phosphate? I got 2. And that is a balanced chemical reaction. So this reaction says that I'm going to take an aqueous solution of strontium chloride and combine it with an aqueous solution of lithium phosphate. I have to do so in a 3:2 ratio. And when I do so in a 3:2 ratio, I'm going to get out strontium phosphate solid. In other words, I'm going to get a precipitate out. Plus, I'm going to get out some lithium chloride, which is still going to be dissolved in water, and I'm going to get out 6 of those. Questions? Now, we can do things like write a balanced chemical equation for the reaction of aqueous lead to nitrate. And aqueous potassium chloride to form solid lead to chloride and aqueous potassium nitrate. Folks, this goes back to knowing how to take your chemical names and convert them into formulas. Lead to nitrate means I'm combining Pb 2+ with nitrate. The ending ATE means it's NO3-. Therefore, the formula for this is PbNO3 because I cross and drop the exponents. I'm combining that with potassium chloride. The formula for potassium is K+. The formula for chloride is Cl-. This occurs in a 1-to-1 ratio, so KCl. These are aqueous according to the problem. That produces or forms or yields or makes, or however you want to say that synonym, lead to chloride. So we have Pb2. and chloride, which is Cl minus, which makes PbCl2. And we are told that that is in solid form. And we also make potassium nitrate. Potassium is K plus, nitrate is NO3 minus. This occurs in a 1-to-1 ratio, so KNO3, and we were told that that is aqueous. So that is our unbalanced chemical reaction. Now I'm going to give you a minute to balance it. To balance it, the first thing I did is I see, okay, I made my list. Then I see, oh, nitrate. I had 2 on the reactant side and only 1 on the product. So I multiplied the product side by 2. When I multiplied the product side by 2, I got 2 nitrate units, but I also got 2 potassiums. So my potassium was no longer balanced. So I had 1 potassium on the reactant side. I now have 2 on the product side. To get the same amount on the reactant side, I multiply the reactant side by 2. Whatever you multiply by becomes the coefficient. So this gave me 2 potassiums, but it also gave me 2 Cl, ultimately balancing this equation. The hard part in that equation should have been taking the names and getting it into the formulas, simply because I know that's a challenge for folks. Because you're still probably memorizing your polyatomics and stuff of that nature. So. Okay. You can see they can get quite complex. In this particular one, when I did a cursory glance, I don't have anything. So I am going to make my list. I have carbon, I have oxygen, I have calcium, I have silicon, and I have hydrogen. On the reactant side, I have 1 carbon. On the product side, I have 2 carbons. Because that 2 subscript means that I have 2 bicarbonate units. On the reactant side, I have 2 oxygens plus 3 oxygens plus 1 oxygen for a total of 6 oxygens. On the product side, I have 2 oxygens plus I have 6 oxygens from the 2 bicarbonate units for a total of 8 oxygens. On the reactant side, I have 1 calcium. On the product side, I have 1 calcium. On the reactant side, I have 1 silicon. On the product side, I have 1 silicon. On the reactant side, I have 2 hydrogens. On the product side, I have 2 hydrogens. This is not balanced. And this one's going to be fun. So the first thing I'm going to do is I'm going to balance out the carbon. Why did I choose carbon over oxygen? Because everything up there had oxygen. You don't want to do that to yourself if you can avoid it. Okay, so I'm going to balance the carbon. On the reactant side, I have 1 carbon. On the product side, I have 2. So I got to multiply the reactant side through by 2. Whatever I multiply by becomes the coefficient. But in so doing, I now have 4 oxygens, 3 oxygens. That's 7 plus 1. That's now 8 oxygens. And look what just happened. I just thought it was going to be a fun one. It was a simple one. Just because they're complex doesn't mean that they aren't easy to balance, folks. Some of them won't be, but a lot of them are. Some of them it's like a puzzle. You're going to have to go back and forth. You try to fit this piece in, it doesn't quite fit. So you wind up going back over here and starting again and going back and forth. But sometimes they are straightforward. But I wouldn't have found it straightforward if I'd have tried to balance oxygen first. Okay, butane gas burns in the presence of oxygen gas to make carbon dioxide gas and water vapor. Butane is one of your alkanes. Its formula is C4H10. Burns in the presence, and that's a gas, burns in the presence of oxygen gas to make carbon dioxide gas and water vapor. And being a vapor means that it's also a gas. This one is probably one of the more complex types you'll have to balance. So I'm going to walk you through this one. First thing though is the same. Carbon, hydrogen, oxygen. We have 4 carbons, 10 hydrogens, and 2 oxygens on the reactant side. On the product side, we have 1 carbon, 2 hydrogens, and 3 oxygens. I'm not going to balance oxygen until last for 2 reasons. Number 1, I have 2 sources of oxygen on the product side. That's going to make my life difficult. And number 2, I have a compound that consists of only 1 element on the reactant side. That's going to make my life simpler if I save it till last. So we're saving oxygen till last. We're going to balance out the carbon first. On the reactant side, I have 4 carbon. On the product side, I have 1. To get 4 on the product side, I got to multiply it by 4. Whatever I multiply by becomes the coefficient. In giving me 4 carbons, I wound up with 8 oxygens from the carbon dioxide and 1 oxygen from the water. So I now have 9 oxygens on the product side. Now to balance out the hydrogen. On the reactant side, I have 10 hydrogens. On the product side, I have 2. To make those balance, I need to multiply the product side by 5. Whatever you multiply by becomes the coefficient. So now I have 8 oxygens from the carbon dioxide and I have 5 oxygens from the water, giving me a total of 13 oxygens on the product side. This is where the fraction initially comes in handy. Because if I multiply the product side by 13 halves, what is that equal to? I mean, if I multiply the reactant side by 13 halves, what is that equal to? 13, because the 2's cancel. So I put a fraction in front of that oxygen. If you go back, though, I said that they have to be simple whole numbers. And if you have a fraction, you multiply the entire reaction through by the denominator. So we're going to have to multiply this entire reaction through by 2. What I mean by that is we're multiplying the coefficient of that entire reaction by 2. So we have 2 methanes, plus we have 13 oxygens, which goes to produce 8 carbon dioxides, plus 10 waters. Check to see if it's balanced. Two times 4 is 8 carbon, 8 carbon. 2 times 10 hydrogens is 20. 10 times 2 is 20. 13 times 2 is 26. You have 16. 8 times 2 is 16. Plus you have 10 times 1, so that's 26. And we can't simplify this any further because they're not all divisible. The coefficients are not all divisible by the same number. Questions? I am going to print off a copy of this particular conversion table or conversion flow chart. I gave you a conversion flow chart early on, but this one adds the density aspect to get to grams for the substance. But when we were developing the coefficients of the balanced chemical equation, what we were developing is another stoichiometric factor that allows us to go from moles of a substance to moles of another substance. In that last problem, if I read the problem, I would have 2 moles of butane to 8 moles of carbon dioxide. That is a stoichiometric factor that would allow us to go from butane into carbon dioxide and convert into something completely new. So again, I do plan to print this off for you so that you have a new table that includes the density, because I do like this table with the density factor involved. But what we were developing as we are going to use is a lead stoichiometric factor. Now, we have not gotten to this piece yet, but we will. By the time we are done with chapter 8, we'll have gone through all of these types of conversions. So, and you can map out whichever way you need to go. With that, I will see you on Monday in lab in 206. We are doing titration. We're getting back to some normalcy.